Hello everyone, in this video we're going to be covering a much requested topic, and that is U-Substitution. And so, what is U-Substitution? Well, say I have an integral that looks like sine of x times cosine x dx. Now, how would you integrate this? Using the formula that you've learned so far? Well, there's no real way to do it. Since you're multiplying this sine of x and cosine x rather than adding or subtracting them, you can't simply just break this into two parts. So you're left with this composite integral that you don't really know what to do with. Well, that is until you have U-Substitution. I'm going to go ahead and write it out on the screen, Salcon style. U-Substitution. And so what it is you're going to take one component of this integral. You're going to write it in terms of another variable, one that we sort of arbitrarily define as u. You're going to take the derivative of that u, and that should give you the equation in terms of this u that you're able to plug back in and solve in a more simple manner. So it should take this composite equation and make it into fewer terms. And so that sounds confusing when you just explain it out, but let me show you how this is done, and hopefully that'll cement the concept in your mind. So with U-Substitution, what you want to look for is terms that are equal to the derivative of other terms. So in this one, that's pretty simple. Cosine of x, as you know, is the derivative of sine of x. So that means we want to make sine of x our u. And what we're going to do next is take the derivative of our u term with respect to x. So you get du over dx is equal to cosine x. And so what you can do now is, since differentials behave like variables when you're talking in algebraic terms, you can move it over to the other side. And now you have cosine of x dx is equal to du. And so now what we can do is plug these back into the equation, but this time in terms of u and du rather than x and dx. So that would look like indefinite integral. Since you have sine of x is equal to u, you can just plug in u for that sine of x, and the remainder is covered by this du, which is equal to cosine of x dx. So now we've got this whole integral rearranged in terms of a different variable that we can now easily take the integral of by using the reverse power rule, which, if you don't remember, is x to the a plus 1 over a plus 1. And so if we apply that to this u, we get u squared divided by 2. Since it's an indefinite integral, we got to put that plus c right there. If it's any integral, we got to put that plus c right there. And so now our final step is to plug these back into the equation to get it back in terms of x. So u squared, u is equal to sine of x, so that becomes sine squared of x. And divided by 2, we just leave that alone, plus c. And there is your integral. But now I'd like to try another example, one a bit more complex. So let me just create a new sheet here. And here's the problem. We want to find the indefinite integral of the sine of the natural log of x, all divided by x dx. So how would we apply U-Substitution to solve this one? So remember, you're looking for items of this composite integral that are equal to the derivative of other items. So what you should notice off the bat is that this is equal to 1 over x times this numerator, sine of natural log x. And you'll remember that 1 over x is the derivative of natural log x. So we already have our u, where u is equal to natural log x. And you can see right away that'll substitute cleanly back into the sign because you'll just have a single variable. No coefficients or powers or anything else to worry about. And now to get our du term, we do the derivative with respect to x, which is of course 1 over x. And then we just bring the dx over, and we get du is equal to 1 over x dx. And now that we have our u and du, we can start plugging back in. So putting our integral in terms of u, we get, there does not need to be an equal sign there, plugging our u back in, we get sine of u, since u is equal to the natural log of x, and plugging our du back in, we get our 1 over x. Sorry about that. We're putting things in terms of u, not x. So our du is also going to account for this 1 over x, as well as the dx, which I forgot to add here. So this big composite integral becomes sine over u du. One single component, just in terms of a different variable. And now we can integrate this. You'll remember the antiderivative of sine is negative cosine of u. And we never want to forget that plus c there. And so now our last step is to plug things back in to get them in terms of x again. So that's going to be equal to negative cosine u is equal to natural log of x plus c. And there you have it. So we've taken this large composite integral that we wouldn't be able to solve by ordinary means, and simply by putting it in terms of a different arbitrary variable, we were able to simplify it to the simple sine of u du and integrate from there. And so hopefully this has shown you the potency of U-substitution in solving these integrals, and has added to your repertoire of knowledge in the field of mathematics. Anyways, that's going to be all for today. Sorry for taking so long with this video. To be entirely honest, I just kind of got lazy and stopped making these, but here it is, after long last. Anyways, I won't keep you any longer. I hope you learned something, and I hope you have a great day.